doesn't make sense. The way, like, it's like the way you have your solution on it just skips over the whole non-homogeneous solution. So I'm like, and I can't remember how to do it, and there's not really like an easy way to Google someone.
There's always YouTube, right?
Yeah.
So for a while, it was like, yeah, it's Jesus, whatever. It's
Also, look at this in the hallway.
没问题，来，你刚才点自动开启。
有了。
我晕。直接被。
Yeah, I just know that it's definitely not homogeneous. I can't like it's like.
反正延迟还蛮严重的，延迟大概半。
就管它。
你坐随便，你坐哪里？这边，这边，这边，或者你坐后面。
最后。
I know that person.
骗死我了。
Oh, yeah. And the lighting is really bright in there. But no, on my side, there are engineers who will to make it because they want to look like but no.
Okay.
Good afternoon. I think we start. I guess this is constantly how many of you will be present in class, right? Yeah, probably we should have more quizzes and less homeworks. Right? Okay. So in the last lecture, we discussed general strategy or general idea to minimize a target function. So suppose our target function is a mapping from a d-dimensional input space to a real value, and parameterized by alpha. Right? This is the input of our function, and we want to minimize this function, meaning that we want to find out a local minimum to ensure that the function value at the local minimum is smallest, at least in a local region. This is the definition of local minimum. Of course, if the function, our target function is convex, then we can guarantee that the local minimum is the global minimum. But in practice, in most of the cases, we're satisfied if we just avoid some local minimum. So the question is that how are the general algorithm steps to find out a local minimum? That's what we have discussed in the entire last lecture, right? So what's the general algorithm steps?
Gradient descent.
Yeah, it's gradient descent. But what's the steps of doing gradient descent? What is the whole process? Let us just review. This is just a review. Any idea? Any hint? So, as that gentleman mentioned, we're performing a gradient descent, right? But what is gradient descent? So you can imagine that we want to find out some location in the input space such that so function value is minimum, right? So to reach that local minimum, we need to give a starting location, right? So if you can imagine, we always start from some initial location in the d-dimensional space, which we can denote it by alpha 0, right? And then we perform some updates, right? Each update move our input from the current location to the next location, right? So alpha 0 to alpha 1, and then maybe alpha 1 to this location, alpha 2, and we continue the movement, right? We continue the adjustment of the locations, and so this is alpha 2, this is alpha 3, and we continue alpha k plus 1, continue until we finally arrive at some local minimum, or at least some location close to a local minimum. This is a general process, right? This is a general optimization, a general algorithm steps to find out a local minimum. We always start from some initial location, right? Then the question is, how can we choose, how can we adjust the locations, right, at each step? So how can we update our input location from current value alpha k to alpha k plus 1. How can we do that? How can we do that? Come on, we just discussed this 2 days ago.
Minus the step size times the f point of alpha k.
Yeah, this updating, or this updates, the rule of these updates, we commonly use is gradient descent, right? So you can imagine in a d-dimensional space, if we move one point to another point, we need to determine two things, right? One thing is along which direction we move. The other is how large step size we choose to move. So in the entire lecture on Monday, we actually identify a very good direction. What's that direction?
Opposite direction of the gradient.
Yeah, exactly right. Opposite direction of the gradient. So we evaluate every time when we do the update, we evaluate the gradient at the current location. Then, if we want to minimize the function, we need to move the current location toward the opposite direction of the gradient, and then along with some appropriate step size. We can denote it by like gamma k. So this rule to update our input locations to ensure that our adjustment procedure to be closer and closer to the local minimum is called gradient descent. This is called gradient descent. And we actually have given a rigorous analysis about why using the negative gradient direction can ensure the decrease of function values. If you still have some impression, we use first Taylor expansion. Use first order Taylor expansion, and we can prove that if our step size is enough small, then it will move along the negative gradient direction. You guarantee the steepest decrease of function value. That's why the negative gradient direction is also called steepest gradient, steepest descent direction. Right? This is something we have discussed in the last lecture, and hopefully after class you can try to recover those induction or derivation by yourself, right? to make your to have some better impression about this piece of knowledge. Right? And then that's one thing, right? The other thing we need to identify is how large step size we need to move. So we have determined that we should move along the negative gradient direction. Right? But how large should we jump? Should we move? That relates to how to determine the step size gamma k. So in the last lecture, although in our rigorous analysis we can prove that when the step size is enough small, we guarantee the decrease of function value. But how small? It's not obvious from the first order Taylor's expansion, right? And the last lecture will give some theoretical results, which can give you a better understanding about the valid range of the step size, but also it's not very practical. So the theory tells us if the gradient of our function, that is gradient, right? So it's a multi-output function. The gradient is actually a vector function. Right? If you have a d-dimensional input, the gradients are the gradient is a d-dimensional vector. Right? So if the gradient of our function is L Lipschitz, so what is the concept of L Lipschitz? Anyone still have some impression? So this is a very fundamental, very heavily used in the area of optimization. So in the future, if in the future you want to take some advanced optimization class, you should be very familiar about the definition of L Lipschitz. Right? So basically, L Lipschitz says that if for arbitrary two inputs P and Q in our input space, the norm of the difference of their gradients is upper bounded by L, this is consistent with L here, times the norm of the input difference. So here are all the default Euclidean norm. So this is called L Lipschitz. So basically, L Lipschitz means that your function values are upper bounded by the change of your function values are upper bounded by the difference of the or the distance between your inputs. That's the intuitive explanation. So if your gradient of the target function is L Lipschitz, then if you choose a constant step size gamma to be less than or equal to 1 over L. So L is related to the properties of your Lipschitz. Right? Then we can guarantee the gradient descent framework converge. So this will give you a first clear boundary about property step size. And then if further our target function is convex, we can estimate the convergence rate. The convergence rate is big O, 1 over epsilon. And epsilon is some specified error. So basically, if I want after k updates, the function value at alpha k is no further away from the local minimum, then the number of updates k is big O 1 over epsilon. This is what we have discussed in the last lecture, right? So we also review what's the meaning of big O notation. So big O notation basically means that, okay, this k is upper bounded by some constant m times 1 over epsilon. So you can imagine if your epsilon is set to be very small, say I want after k updates the function value, difference between the function value and the minimum of the function value is less than or equal to, say, 10 to minus 6. Then the number of updates is at least 1 million. Right? Of course, if you set up a smaller, larger error, say, I think 0.01 is pretty enough, and then maybe just 100 updates is good. Right? You are not necessary to take so many gradient descent updates. So this is for the general convex function and gradient. If you use gradient descent to minimize the general convex function. But then later we discussed a special type of convex function. It's called a strongly convex function. So what is a strongly convex function. So you don't need to memorize the inequalities, definition inequalities, but I hope you have already had some visualized impression. Right? We have discussed the visualized impression of all the strongly convex functions. Right? That is much easier to memorize. Right? So basically, strongly convex function means that you have a tighter lower bound. Right? Show that. So suppose this is a strongly convex function. So for general convex function, we can construct a lower bound of the function by using the tangent line of your function at any point. You can try it. You can just draw a tangent line at any point of the input. You will find that there are always a lower bound of the whole function. Strongly convex tells that we have an even better lower bound than this tangent line. We actually have a quadratic lower bound, meaning that there exists some quadratic function, which is also the lower bound of the total function. That's how the definition of strongly convex function comes from. So if right now I write down the definition, it won't seems that annoying, right? So basically, if we say a convex function is eta strongly convex, it means that for any input p and alpha, we have this is a function value, right? And then we write down this quadratic lower bound, which is alpha plus the first two terms in the quadratic lower bound is just first order Taylor extension, so it is alpha transpose difference between p and alpha, and then plus a quadratic term, which is eta over 2 multiplied p minus alpha and take square norm. So this is the definition of the eta strongly convex. So you can see that this first two term is actually a linear bound, the tangent line. And then strongly convex says that in addition to this tangent line as our lower bound, we actually can add one more quadratic term. So obviously, this whole right-hand side, this is a positive term. Right? It's bigger than the first two terms, meaning that we have a quadratic lower bound on the right-hand side. This is called strongly convex. So why would we like to hear about the strongly convex? We mentioned in the last lecture, actually many training objective is simply strongly convex, like SSE, right? Sum of square error. If you arrange them into matrix vector operations and you test them with condition, you find that they're strongly convex. So now, if our target function f is strongly convex, and eta is strongly convex, maybe it's too messy. So if our target function f is eta strongly convex, and the gradient of f also Lipschitz. And we can choose the step size to be less than or equal to 2 over eta plus L. So this is properties from two conditions, right? And we can guarantee converge. In addition, our convergence rate is improved much. Our convergence rate now becomes a logarithm of 1 over epsilon, and epsilon is the designated error. So we find that if our training objective happens to be strongly convex, even use the simple gradient descent, you can converge to the local minimum or also global minimum because it's strongly convex very quickly. So, although this theory gives us some insight about what is the valid range of step size for different types of functions, but actually they're actually not practically useful because you don't know how to identify L, given your gradient function is Lipschitz, and you don't know. Sometimes you even do not know how to identify eta. Right? So it is impractical to use these theories to help you to identify appropriate step size. So in practice, we generally use another type of methods called line search. So in the last lecture, we don't have time to cover it, and I asked you to read the course material, which is pretty rough, but I don't really want you to skip that. Right? So just to give you an impression, what is the process of line search? So the basic idea is as follows. So currently we are at alpha k, right? And we know the gradient at alpha k. So the question is, how can we find out the appropriate step size gamma k, right? An intuitive way is to directly optimize this function, f alpha k minus gamma k times the gradient at alpha k. So if you fix alpha k, the current location, and also fix the gradient at alpha k, right? So this actually becomes a function of gamma k. We can denote it as another function. So to find out the best step size gamma k, we can simply minimize this single variable function. Right? We can directly minimize gamma k to find out the optimal step size. And then when we find out, we just update it. Right? So this is a very straightforward way to find out the gamma k. But doing this is problematic in several special cases. That means if you use this method, you cannot guarantee every time you're gonna make your whole gradient descent procedure reach the local minimum. There are special cases such that if you use this method to identify best gamma k every time, your update could be oscillate for some particular case. And what kind of particular case we don't have time to disclose here, but there are some particular cases. So exact line search actually is not perfect. In practice, people usually develop inexact line search, meaning that we're not trying to really minimize this function of gamma k. We just try to find out gamma k to decrease the function value, but satisfy some condition. If that condition is met, then we just stop and find and return current gamma k. We don't really minimize this function of gamma k. And by using this set of conditions, we can guarantee the gradient descent will finally end up with the local minimum at any situations. So there are many different conditions. So like Frank-Wolf conditions. So if you take a optimization course, you will learn that Frank-Wolf conditions or other conditions, and it's pretty strange. If you take a look at the setting of Frank-Wolf conditions, usually it's very strange and it sounds like heuristics. But interestingly, by using that kind of heuristics, you will early stop your searching of gamma k. It can guarantee the convergence of your general gradient descent. And also there, as mentioned in the cost material, there's another method called ghost section search. So basically, the idea is that this is a whole region of gamma k, and they just want to break the region of gamma k into several segments. And they just identify one of the segments that contain the optimal gamma k. That's it. We don't want to further drill down to find out in this particular region what is the best gamma k. I just find out some gamma k in this region. Then we stop. It's called ghost section search. And another commonly used method is called backtracking search. But they are all line search methods. So basically, I assume I start gamma k from 1. And I assume I choose a damping factor, say beta, between 0 and 1. So every time I just dump beta k by the factor beta, gamma k by the factor beta, until some stop condition is met. Then we finish. So this one, the backtracking line search method is easiest to implement because every time you just need to multiply the current gamma k with damping factor, right? You just need to choose the damping factor. And also there is a rigorous proof that by using this backtracking method, you will end up with convergence. So any questions so far? Okay. And our task today is to investigate the gradient descent, the usage of gradient descent to learn our regression model. So in the previous lectures, we introduced the concept of regression, right? So we assume that we have one single or several explanatory variables, x, right? And to include the case that we have multiple explanatory variables, we can assume x is a vector, right? I put an arrow to emphasize x will be a vector, and we want to use those explanatory variables to predict our target variable y. This is our regression model. Of course, we need to assume y is continuous. This is called regression. Otherwise, it is classification. And then to make the prediction, we need to first specify a regression function. So we assume a regression function of x parameterized by alpha. We use this regression function to predict y. And then different regression function determines different regression models, right? So we introduced the linear regression. So what is linear regression? What is linear regression? It's just a linear function of x, right? So for linear regression, it's a form of a regression function. It's simply the inner product between our parameter vector alpha and what? Yeah, input data, right? Input vector. And here, the input vector, we need to augment the input with 1, right? Because the alpha, the parameters in alpha include a intercept. Right? This is for linear regression. And if we use a polynomial regression, then the regression function is a polynomial function, right? And the alpha now becomes the coefficients of the polynomial terms in your polynomial function. And now, given the regression function, and also we assume we have collected a set of training instances. Right? So training instances consist of pairs of explanatory variable values and target variable values. So suppose we have collected n training instances, which denoted by x1, y1, x2, y2. I should use x3, y3 until xn, yn. And then we want to fit our regression model to the n training instances. This is called training or model estimation. Right? And how can we fit them? How can we fit training instances? An idea? Come on. Any hint? Yeah, SSE, right? We need to come up an objective function, right? Objective function which include all the training instances. Right? So up to now, we only talk about one training objective, that is SSE, sum of square error. Sum of square error is summation of all the errors over each training instances. Right? So inside this summation, we use our regression function to predict the target variable, right? Then calculate the square error, and add up all the square errors with SSE. So we know that right now, because the training data are observed, meaning that each xi and yi are fixed, right? So essentially, SSE is a function of what? Yeah, alpha, right? A function of alpha. And we minimize SSE to obtain the best alpha. This is called fitting. This is called why we should choose the best model that fit training instances. That is, we choose the best model parameters alpha to make SSE to be the smallest. This is called fitting. So this is the general procedure. And how then the next question would be, how can we minimize SSE? How can we do that? How can we do that? What's the general strategy of doing this?
Taking the derivative and set it to 0.
Yeah, this is the previous strategy we have discussed, right? But what if your regression function is very complex? If you take the gradient and set to 0, you cannot solve that.
Could we use gradient descent?
Yeah, that's why we introduce gradient descent. Right? So in the case that this objective function is very complex, we don't have analytical solutions, but we still want to find out some model parameters, make SSE to be as small as possible. Then we use algorithmic steps to optimize it. That relates to the gradient descent framework. So in general, we can use gradient descent framework to find out the best alpha. So this is the whole procedure. You can see how do you build up a machine learning model, how do you ask model parameters, how do you learn it. This framework, this process explains all. Right? You come up a regression function, you collect the training instances, you form your training objective function. In our case, is SSE. Then use gradient descent to minimize SSE, the objective function, to find out the best model parameters. Any questions so far? And this not only applies to like linear regression and polynomial regression we just covered. Right? This actually applies to any model you want to use. you can use very complex regression function. For example, neural nets. Then in the neural nets, you can imagine this alpha will be the width of the neural units. Your neural nets, right? You have a very deep layers neural nets. Or you can use any other method. So now let us do some case study. Let us do some detailed study. Right? We still use the regression model we discussed before. We use polynomial regression. That means we assume our input is just a scalar. We assume our input is just a scalar, so we do not need to put an arrow on that to ensure to emphasize this vector. And then what kind of polynomial do we choose? I assume that we know the best order. We assume, okay, our polynomial regression model is just a second order polynomials. So what's the regression function? What's the regression function?
The 0 plus alpha 1 x plus x squared.
Yeah. Second order polynomial, right? So we have the first term must be alpha 0, which corresponds to the 0th order polynomial term, right? And second term is alpha 1 x, first order polynomial term. Alpha 1 is coefficient, right? And then second order polynomial term, alpha 2 x squared. So this is our regression function. And again, assume we have collected n training instances, meaning that we have n pairs of x values and y values. Then our next objective would be what? Our next step would be what? Just follow the framework we just mentioned, right? We formulate the SSE, right? We just plug in our second order polynomial into here. Then we get our SSE. Then we use gradient descent to find out the best alpha, which corresponds to alpha 0, alpha 1, alpha 2 here. Right? So for simplicity, let us first assume our number of training instances is just 1. So meaning that we have only observed 1 x and y values denoted by x1, y1. Right? Then what is our SSE? We can denote this SSE for the x1, y1 by SSE1. Right? It's just the sums of square and row on the first training instance. So then what's the SSE here? Any idea?
Just the error at that for that data point.
Yeah. But so remember, we assume we only have 1 training instance, right? So the SSE is just 1 square error, right? So it is L alpha x1 minus y1 t squared. 0 SSE1 on a single instance. And then we can take the gradient with respect to alpha, right? So here, alpha is what? Alpha 0, alpha 1, alpha 2. And if we want to use gradient descent, we need to compute the gradient of our objective function. So remember, this is a function of alpha. Then let us do the gradient, take the gradient. Right? So the gradient of the SSE1 of alpha, we can try to do first do the scalar gradient. So which is the partial derivative, or say alpha j. So alpha j would be 0, 1, 2, right? Because we only have 3 coefficients here. So if we take partial derivative over alpha j, so according to the chain rule, we first take the derivative of this square sum, which is 2 times the difference between our prediction and true value, and then take the partial derivative, this chain rule, partial derivative of our polynomial function over alpha j. Right? So we can observe that no matter what kind of j you choose, this coefficient does not change. Right? It's invariant because of the chain rule. Right? You got first take the derivative over the square term, and then take the derivative of the regression function, the polynomial. So we can check what's the result for the second term. That is partial derivative of our polynomial with respect to different coefficient. Right? So what is the partial derivative? What is the partial derivative of our second order polynomial to alpha 0? Just 1, right? And what about the partial derivative with respect to alpha 1? X. But right now, we're instantiate our polynomial with x1. Right? So actually, this is x1. Okay. And what is the partial derivative of our regression function at x1 with respect to alpha 2? Just here, right? x1 squared. x1 squared. So let me write down everything clear. So now, given the partial derivatives of our regression function with respect to all the parameters, right? We can actually obtain the gradient vector. Right? We can directly obtain the gradient vector, which is what? Remember, each partial derivative, all the partial derivatives share the coefficient here. That is 2 multiplying with the difference between the prediction and the target variable value. The only difference is here, right? And now we can we have the results. We have a result for the second term. And now if we combine them together, integrate them together into a vector, we end up with our gradient vector, right? So what's the gradient vector? And then multiply with this, right? So let me write down explicitly, right? So it is simply 2. It sounds not clear right in the bottom, right? So from here, we can directly generalize to the calculation of the gradient vector. This term is shared by all the partial derivatives. So just move here. It's 2. x1 subtracted by the true value. And then we just substitute the partial derivative by the vector, by the gradient vector of the regression function. So simply copy 1, x1, and x1 squared. And now ends up our gradient vector. So in this way, we finish the computation of the gradient. And then we use the gradient to update alpha, continuous update alpha. until we reach the local minimum. Right? So this is just for one training instance, meaning we will observe x1, y1. Right? So now what if we have n training instances? What if we have n training instances? How can we compute the SSE of n training instances? And their gradient. So first we can observe that the SSE over all n training instances is what?
Sum of each individual.
Yeah.
SSE.
So actually, it is simply SSE1 alpha plus SSE2 alpha. And continue, right? Continue, we are continue SSN alpha, right? Now to calculate the full gradient, what should we do? To calculate the full gradient of SSE, what should we do? Is this question too easy? This is very obvious, right? We have a knowing how to compute the gradient for the SSE on a single instance, right? So now we want to calculate the gradient of the summation of all the SSE. How can we do that? We just add all the gradients together. Right? That means we need to compute n times. For each instance, we need to compute the gradient of its associated SSE, right? And finally, we add them together, we end up with our full gradient of the SSE. And now we can use gradient descent to minimize our SSE to find out the best alpha, right? So let me just write down the pseudocode. So it is gradient descent this is our SSE function, and we need to indicate a starting point, right? And then we initialize of 0 to be the starting point, and the number of updates right now is 0. Then we continuously perform the gradient descent update. So alpha k plus 1 will be alpha k minus some step size multiplied with the gradient descent, the gradient direction, right? And we'll continue to do this until some stopping condition is met. For example, the gradient of a current SSE is smaller than or less than some tolerance level, tau. Right? So this is an algorithmic framework for us to learn our second-order polynomial regression model. Right? So this algorithm is called batch gradient descent. Why is it called batch gradient descent? Because for each particular update, the computation of the gradient needs to go through all of the training instances. So we can analyze what's the computation complexity. So for each update, what is the computation complexity? Any hint? For each update, meaning that if we want to execute one operation here, what's the computation complexity? Actually, the computation, what determines the computation complexity?
Dimensionality of data, the number of data points you have.
Yeah, excellent, right? So let us just forget about the dimension of the data you have, because right now we're just focusing on like second order polynomial regression. Your input dimension is at most 3, right? So then the computation of the updates is mainly determined by the computation of the gradient, right? And then to get the gradient, what kind of calculations do we need? We need to calculate the gradient of SSE1, SSE2, until SSEn, right? Basically, how many training instances you have, how many calculations you need to perform. Right? So that means the computation complexity is O(n), right? Proportional to the number of training instances, or in other words, the size of your training data. So that might sounds okay for you because it is linear to the size of training data. It sounds okay, right? But imagine in this time of big data, the number of training instances would be incredibly large, like a billion or a trillion. So sometimes your laptop, your desktop are not even able to finish the computation of one gradient. Right? That means when the number of training instances is very large, it might be infeasible for you to finish one gradient descent update. This is definitely unfavorable, right? We don't want that to happen. Also, you can imagine that when the number of training instances the cost to perform one single update could be very high. You need to go through all of the training instances. So then there naturally comes out a question: can we reduce the cost of computing the gradient such that in less time we can finish much more updates? So can anyone, just a wild guess, can anyone come up with some idea to reduce the cost?
Guess randomly.
Yeah, guess randomly. Yeah, you can guess randomly, but in that case, if it is too randomly, you are now guaranteed to decrease your objective function. That's not useful. Right? Any other guys? Another conjecture.
You could maybe lower your batch size so you're not going through every single training example, or also vectorize computing the gradient. So like if it runs on a GPU, you can compute them all at the same time.
Yeah, both of your ideas are excellent, are great. It's actually widely adopted. So first, you can increase your computation power, right? If you have GPUs, you have computing clusters, you can distribute your computational amount into many computers. That's one way. Right? Another way is more important. This is what we are gonna discuss, right? So that how about we give up some training instance when we compute the gradient. So that sounds pretty straightforward, but it actually works. So let us introduce the first variant of gradient descent. It's called incremental gradient descent. So what is incremental gradient descent? Again, we initialize our alpha at the beginning with some starting point. And then we set up an index of instance. So basically, every time to get the gradient, I do not go through all of the training instances. I just pick up one instance and then calculate the corresponding SSE and its gradient. Use that gradient to update. So incremental gradient descent means that I just try to pick up the first instance and then second instance, third instance, and fourth instance, and continue. So here is logic. So we do the also we need to set up the current update is 0, and then to perform our update, we simply calculate the SSE on the ith instance and compute its gradient at alpha k and times a step size gamma k. And here we should update the update number, and also we should update the index of the instance we next will choose. And we can do that until, of course, the norm of the gradient is less than or equal to some specified tolerance level. So this is called a incremental gradient descent. So in the first update, we simply choose the first instance, calculate SSE1 and its gradient, and use this gradient to update our model parameters alpha, right? And then to perform the next update, we choose the second instance, and then calculate the gradient of SSE2, and then update the current alpha. And you can continuously do that. But if the number of updates exceeds the number of instances, we just go back to 1. And that's that's what's the meaning of this line of code. We do them all. Right? So if the instance, if index is bigger, is bigger than n, you just mod n, you go back to 1. So any question about this algorithm procedure? It's pretty straightforward. And by only calculating the gradient of SSE on a single instance, meaning that we only pick up one term for the gradient computation, we can dramatically reduce the computational cost. Right? So now, what is the computational complexity to perform the incremental gradient descent? What? O1. Yeah, O1, right? Because we're going into compute the gradient with respect to one training instance. So more general step is that why not we need to strictly follow the order of instance. Right? So how about we just random pick up the instance every time? We do not specify some particular order to go through every instance during updates, right? We just random pick up the instance to compute the gradient every time. This algorithm is called stochastic gradient descent. So what is stochastic gradient descent? Just copy every step here, except that every time I choose I randomly. That is index an instance randomly from the range 1 to n. And then you compute, then you just move here. You compute the corresponding SSE of that instance, the gradient, and use that gradient to update the current parameters alpha k. And next time, you'll random pick up the index of instance again. And then you use you compute the corresponding SSE, the gradient, and then update the parameters and continuously until convergence or some tolerance level is reached. This is called a stochastic gradient descent. And this is now very widely used, although it looks quite naive, quite straightforward. And for both incremental gradient descent and stochastic gradient descent, we can know that the computational cost to perform each update is just O1. So you can imagine it will be much cheaper to perform updates. Even if you have billions of training instances or even trillions of instances, you can perform many updates like using your cell phone. Because every time you just need to pick up one instance, compute the gradient, update.
What's the disadvantage of using those as opposed to using just like naive gradient descent?
Yeah, that's a very good question. That's something I want to ask you right now. Of course, there's no free lunch, right? What's the benefit? The benefit of like incremental gradient descent or stochastic gradient descent is that it is very easy for us to perform update, right? But what is the disadvantages?
It's not exact.
Yeah, it's not exact. It's not right. So we know that from our proof, right? From our Taylor expansion, from our analysis, we know that if we follow the exact gradient, we can guarantee our target function to get decreased after each update. But now, we just pick up one term in our original target function, calculate that gradient to update. Then what will happen? Then what will happen? First, it is not that obvious if you perform an incorrect gradient. If you use incorrect gradient to update, you can guarantee the function to decrease every time, right? Actually, there is no guarantee for that. So you can imagine. Here is our current position of k, right? And here is our local minimum. And we know that if we calculate the true gradient, that means we have to perform a very costly computation because we need to go through every instance and compute the gradient of the corresponding SSE and add them together. But although it is costly, we can guarantee that after update, our position is closer to the true local minimum, right? But now, if we use a stochastic gradient descent or incremental gradient descent, every time the gradient we use is wrong, is incorrect, then we cannot guarantee after the update using incorrect gradient, we'll still get closer to the local minimum. It actually could be here, could be here, or could be even further. All are possible. All cases are possible. But then the question would be, if we perform many such kind of cheap updates, although sometimes they're even wrong updates, right, or ridiculous updates, can we finally end up with at least some location closer to the local minimum? And fortunately, the answer is yes. And the analysis or the proof for this is highly non-trivial. But there is some conclusion. I guarantee that if you perform stochastic gradient descent, and if you choose your step size gamma k following some protocol, basically it must be decaying, meaning that when the number of updates increases, your step size must become smaller and smaller. And also, if you can write down the sequence of step size must be converged, and whatever kind of conditions, you can guarantee finally you have a large chance, you have a high probability to arrive at some local minimum. So why we never say we guarantee to converge to a local minimum? Because this is the stochastic gradient descent. If you analyze that, you must give some probability. This time you run the stochastic gradient descent, it's different. The result is different from next time you run the stochastic gradient descent. But there indeed is such a kind of proof. The other question would be, which one or which kind of methods can move faster to the local minimum? Now that both the batch gradient descent, our classical gradient descent, and stochastic gradient descent can converge to the local minimum, then which one will take fewer steps? An idea? Any guess?
On average, probably batch gradient descent, right? Because you know that you're moving in the exact right direction every time.
Yeah. Very intuitive, right? Obviously. And because I follow the correct direction, why should it be slower than those crazy guys? Right? So, of course, if you perform the exact gradient descent, that is the batch gradient descent, you will take much less number of steps to arrive at the local minimum. If you take stochastic gradient descent, you're like a drunken driver, right? You are randomly drive along north and northeast and west and whatever. Finally, you end up with a high chance to arrive at your home with a crashed car, right? But this is just a high chance. But you can imagine you might have go through very wild paths to arrive at your home. Right? So you can imagine the number of updates required for stochastic gradient descent to arrive at local minimum is much larger than the batch gradient descent. Then the question, the interesting question is here. Then why should we still prefer stochastic gradient descent? I can tell you in large data sets, stochastic gradient descent is much more widely used than the batch gradient descent.
I think it's because you could converge without going through the whole data set. But if the updates led you to the right place.
Yeah, that's one reason. Any other thinking? The answer is kind of more more in depth. Actually, I want a more intuitive or obvious thinking.
Gradient descent is only an estimate in the first place, so taking a computationally heavy route may not be the best way. You can achieve the same or near the same answer with a less computational heavy answer.
That's the right part. That's because it is cheaper to compute, right? So if you want to perform the batch gradient descent, when the size of trained data is is very, very large, and sometimes you even don't have enough powerful device to finish the computation. You're even infeasible to perform only one update. But if you use stochastic gradient descent, no matter how large your data set is, you use your cell phone to do that. It's pretty okay. And if you have enough, you have a good battery or you keep it in charge, then finally you end up with some gradient descent. So it's cheap. Everybody can use that. That's the one reason. And the other reason is kind of empirical. And right now it's still an open problem. The other problem is that in many non-convex, high nonlinear training objective, empirically stochastic gradient descent performs much better than batch gradient descent. That's an interesting observation, but no one can explain right now. So up to now, those elegant properties and beautiful conclusions are based on the assumption your function is convex, right? But in practice, in the future, you might turn to like TensorFlow, those kind of steps. You will build up highly complex neural nets. The corresponding objective function, let us write another SSE, is obviously not convex, and is very, very complicated and could contain many, many local minimums. For example, I can randomly draw a function curve could be like this. You have many, many local minimums. Right? Here is one, the other, the third, right? It turns out that if you use stochastic gradient descent, you will have a larger chance to arrive at better local minimum, mean that deeper value. See here. If you use a batch gradient descent, it can converge faster at smaller steps, but it often converges at those bad local minimum. I have some kind of guess to explain why. You can imagine, because stochastic gradient descent is a kind of wild drive, right? You jump wildly. So at the beginning, if there is some bad local minimum, inferior local minimum around you, you have a large chance to skip it, because you are at the beginning you are always jumping wildly. And finally, because your gradient descent, your stochastic gradient descent, you have to make your step size to be smaller and smaller. And finally, you might end up with some places at deeper values. But this is just my guess. This is just my guess. And in the future, if you are going to train a deep neural nets, stochastic gradient descent is the standard method. No one is going to use batch gradient descent. So this is mainly two reasons why stochastic gradient descent is so popular. But for you to understand right now, all you need to know is that you should be clear that the trade-off that can be expected from the two methods, the trade-off between the cost of computing one update and the number of the updates to arrive at the local minimum. If you use batch gradient descent, okay, each step you jump a larger, more successful step, which is closer to the local minimum. But to finish this step, you have to spend a lot of cost. Right? You have to use a lot of computational power. And if you use the category descent, if you want to jump one step, it is very cheap, very easy, very fast. But it does not guarantee the quality. So you can perform many cheap costs, but you have to do a lot more cheap updates to arrive at the same local minimum. So this is a trade-off. It's just a trade-off. And in the optimization theory, to compare these two methods, there's actually no goodness and badness. And the usage is mainly the preferences of the usage is mainly in the practice. Okay, I think we should stop here.